Okay, so I may have a workaround now for this pen problem. So let's see how this goes. So let's go back to starting from this image. Now, one small thing is that this image and this image seem to have a different size or different shape. But that's because this image has the color bar on it, so the image is a bit squashed. And the other images here don't. So that's the only real difference in the size. But this image here is produced by applying this Gaussian mask by convolution to this image here on the left. So you can see the result is that you have a slight degree of blurring. To go from this image to this image, we again apply this convolution mask to this image, and that gives us this result. Then we repeat applying this convolution mask to this image to get this result, and so on. So there's a cascade of operations that allows us to go from this unblurred image to this image on the right hand side, lower bottom right hand side. So this image has the highest degree of blurring within this stack of images. So how do we represent this as a sort of a computational flow? So let's have a look at our board scene, which we hope will now allow us to represent this a bit better. So I'm going to start off by thinking about the original image here. So this is our original, and we're going to call this f as a function of m and n. And what we do is we take this image and we apply a convolution routine. So let's just represent that with conv. And the result of that, let's stick our arrows on here to indicate a flow, is going to be a blurred image. And we're going to call this particular image, we're going to label this f1 with the little brackets there as a function of m and n, which represents our first scale of blurring. So by that token, we can represent this as f0, which is just the original image. Okay, so that's just a notational thing. Then we take this image and we apply, so the output of this conv routine, by the way, this is our mask mg. So the output of this, we again apply a mask mg, and the output of that we label as f2, as a function of m and n, and the output of this we again drop into another conv operation, again with the same mg, and we keep on repeating that process, getting our successively blurred images. So you can see that this is now a cascade of convolution operations, each of which produces a result that is of interest to us because it represents a different degree of blurring of the original image. Now what's interesting is that all of these masks are the same. So in all cases we're using a 3x3 approximation to a Gaussian. So that's a 3x3 mask, a 3x3 mask, and that's also a 3x3 mask. But the effect of cascading these convolution operations is that by the time we get to, let's say, this image here, the third image, we are effectively blurring our original with a much fatter Gaussian mask. So the relationship between this image and this one can be described as, again, by convolution, but rather than with a 3x3 mask, it'll be a convolution with something like, it's going to be a sort of an 11x11 mask. So the exact calculation is escapes me, but hopefully you get the idea. So that gives us an introduction to what we can describe as a layered series of convolution operators, and that is similar to something that we might use we might have in a deep neural network, which is an input image goes in at one end, and then you have convolution followed by convolution followed by convolution. Now, in fact, in a deep network, we don't use a single mask. We actually have at every layer, we have multiple masks being applied. So we're going to see where that comes from next, or further on in this lecture. So let's move on now to looking at another type of mask. So the Gaussian mask gives us a degree of smoothing. And any mask that has the same sign of values, so all the values in the mask coefficients are the same, you get some type of smoothing. For the case in which you have differences in the sign of the coefficients, then the effect of convolution, because you're multiplying the mask values by the pixel values and then summing, the effect of something like this is going to be similar to the effect of something like a derivative. You're looking for changes in intensity across the image. And strictly speaking, what you're looking at is these positive and negative values will be weighting pixels in opposite signs, so that when you sum, you're emphasizing differences, or differences contribute to the output of the convolution mask. So one of the operators we can look at is it's a very crude high pass. It gives you very crude high pass filtering of the image, and again this can be achieved by convolution, and in this case the mask would look something like this. So let's have a look at the result of that operator. And what I've done here is taken the mask that's been blurred to the image has been blurred to the largest extent in that sequence a few pages back, so this image here, and applied this mask. And what you can see is that in going from this to this, we have the opposite of a blurring effect. We have a bit of a sharpening effect. You can also see that in the same way that the smoothing operator enhanced the brightness of the large structure of the leaf against the fine structure of the background, here we have this slightly the opposite effect, which is that the contrast of the leaf against the background has been reduced. In fact, the brightness of the background seems to have been amplified, and that's because we still have a high frequency content at the background that we do within the leaf. And so you get this effect of even things like the veins of the leaf are beginning to reappear. Now, you can't completely recover all the information from this image to go back to the original, but you can see that there is a certain degree of sharpening in going from this image to this image by applying this mask. Okay, so again, the feature that you see about this mask is that there is this there are different signs present within the mask. So negative and positive values are both present. Okay, so the next question you may ask is, well, how are the mask values set? And one of the ways that we can think about this is to look at a very specific problem that is inspired by continuum mathematics, that is the mathematics of functions over a spatial domain. And in particular, what we're going to remind ourselves of is something that hopefully several of you will have met, which is it's sometimes referred to as the del operator. So it's that operator here. And that operator, when applied to a function of two variables, so a scalar function of two variables, converts that scalar function of two variables, or maps that scalar function of two variables to a vector field as a function of two variables. So we shall look at that next.